Hi, my name is Bella.
Hi, my name is Alexjandra.
Hi, my name is Michelle. Our inspiration for the project was we enjoyed dilution and we enjoyed titrating. We wanted to combine the two together.
Our experiment was the effect of changing the concentration of sodium hydroxide on the amount necessary to neutralize sulfuric acid. The independent variable is the concentration of the sodium hydroxide base in the levels of 0.10 molarity, 0.50 molarity, and 1 molarity. The dependent variable was the amount of base necessary to neutralize the acid.
The control variables were 10 milliliters of 0.50 molarity of sulfuric acid and 2 drops of phenolphthalein.
Our research question was, what is the effect of the concentration of the base sodium hydroxide at 0.10 molarity, 0.50 molarity, and 1 molarity on the amount necessary to neutralize sulfuric acid?
Our hypothesis was that if the concentration of base increases, then the amount necessary to neutralize the acid decreases.
Gather your materials. You need 1.67 milliliters of 3 molar solution of sulfuric acid, 40 milliliters of sodium hydroxide, a Erlenmeyer flask, a burette, a 15 milliliter graduated cylinder, safety goggles, 50 milliliter beaker, and a pipette. Next step is diluting the 1 molar of sodium hydroxide into a 0.10 molarity. Measure out 4 milliliters of sodium hydroxide. Once the 4 milliliters is measured in a graduated cylinder, you're going to pour that amount into a volumetric flask. Then you're going to pour distilled water into the volumetric flask into the 100 milliliter line. From there, you can use a pipette to exact your measurement. Secure the cap and gently whisk around until the solution is diluted. Put the solution aside and we'll attend to it later. Next, dilute the 3 molar solution of sulfuric acid to a 0.50 molar solution using 1.67 milliliters of acid. Put the diluted amount aside and we'll attend to it later. Next, you are going to take the amount you diluted of 0.10 molarity of sodium hydroxide. Measure out 40 milliliters of the diluted solution and pour the amount into a burette. Then record the initial volume. Next, take your sulfuric acid of 0.50 molarity that you put aside and pour approximately 10 milliliters into a graduated cylinder. Pour the 10 milliliters of acid into an Erlenmeyer flask. Add 2 drops of phenolphthalein into the solution. Then, place the Erlenmeyer flask under the burette. Slowly add in the base by whisking around the Erlenmeyer flasks. Notice as the base comes in contact with an acid, a bright pink color is shown. Keep this process going till a bright pink color stays for 10 to 30 seconds. Repeat the steps in order to have 2 more trials for the 0.10 molarity. The process using 20 milliliters of sodium hydroxide to dilute it to a 0.50 molarity. Then use 40 milliliters of sodium hydroxide for the 1 molarity solution.
We did different concentration of sodium hydroxide, which are 0.10 molarity, 0.50 molarity, and 1 molarity with uncertainty of plus or minus 0.05 milliliters. We did 3 trials to get the initial volumes and the final volumes for each molarity. The equation in this is sodium plus sulfuric acid, or the reactants, cause the products of sodium sulfate and water. The sodium chemically binded with the sulfuric acid to become neutralized. Water was formed by the hydrogen and oxygen combining. This next part of the calculation shows how we subtracted the final volume from the initial volume to get the amount of base used. We averaged each trial together in order to find the average amount of base used.
The graph for our experiment shows a downward trend. As the concentration of base increases,
the amount of base used to neutralize the acid decreases. This shows the equation molarity of acid times the volume of acid equals the molarity of base times the volume of base to find the experimental molarity. We got 0.235 for the first experimental molarity, 1.16 molarity for the second independent variable, and 3.76 molarity for the third.
In the experiment, we hypothesized if the concentration of base increased, then the amount of base necessary to neutralize the acid would decrease. This is because as the solution becomes more basic, it will take less of the base to neutralize the solution to have a pH of 7. It takes a less amount of a stronger base to match the molarity and volume of a weaker acid. The findings support our hypothesis because on the graph the acid requires an average of 21.29 milliliters of 0.10 molarity of the base solution for the acid to be neutralized. Then at 0.50 molarity, it took 4.30 milliliters, and then finally at 1 molarity, it took 1.33 milliliters to neutralize the acid.
The first level of our independent variable at 0.10 molar solution, we experienced a high level of error of 135%. For the second level at 0.50 molarity, we experienced 132%. And for the last level of our independent variable at 1 molar, we experienced 276% error. Yikes. One procedure error is not being able to determine the precise endpoint. Each individual perceives color differently. There's no exact measurement to find the endpoint. This affects the data because too much of base could be added into solution, increasing the amount of base used, or not enough base could be added into the solution, decreasing the amount of base used, making the solution more acidic. In order to eliminate this error, we would include more trials to find a more accurate and precise amount of base used. Another source of error was not diluting the base to the correct concentrations. For example, we got a 0.235 molarity compared to our actual amount of 0.1 molarity. The molarity was more concentrated than we wanted. This is because the sodium hydroxide we started with had a greater value than 1 molarity. The greater value was caused by the original dilution from 18 molarity to 3 molarity, and then from 3 molarity to 1 molarity. During this process, there's lots of uncertainty in measuring out the volume. Having a higher molarity causes less base to be used to neutralize the acid. It decreases the data values. In order to eliminate this error, you could use a conductivity probe to measure to see if it's the correct molarity. You could also do the dilution in one process in order to decrease the amount of uncertainty produced in each dilution.